Okay, this is the first 2 pages of the notes. We're going to be looking at solving 3 different systems of equations. This is example 1, and then example 2 and 3 are going to be on the next page, and then that will lead us into stating some general definitions. And when we get to that part, we're going to split off to the next segment of this video. I am recording these in smaller segments so that you can more easily navigate around and just listen to the parts that you need. If that's not the case that you need to do that tonight, certainly for review, oftentimes it's nice to be able to skip to a particular part fairly quickly and see again the instruction that went with just a part of the lecture. Okay, so this lesson is on solving systems and writing solutions. And what I want to do here is to take this system of equations and solve it in a way that looks a lot like you might have done in high school. And so what I'm going to do is just copy this out right here. And we're going to be writing things in a different way soon enough so that it really won't look much like this at all. But this is a way to get started, and then I'm going to show you how this is reflected in another way we might work on this system of equations. Now what I'm going to do is I'm going to take minus 2 times this equation and add it to the second equation. The reason for that is I'll have minus 2x plus 2x, that'll give me a 0, and then this the resulting equation for the second line here will have only 2 variables in it, y and z, rather than 3 variables, x, y, and z. And that's an advantage. Now, you don't need to do this, but it helps me. When I'm multiplying through by a constant, I like to just kind of write it off to the side, and then I don't forget what I'm doing. So I have minus 2x plus 2x is 0. Of course it's 0. That's why we're doing this. But the rest of these columns we really do need to work on. Minus 2y plus 4y is 2y. And then minus 4z minus 3z makes minus 7z. And minus 18 plus 1 is minus 17. And that gets our second equation. Okay, for the third equation, I'm actually going to modify this. I'm going to take minus 3 times the first equation and add it to the third equation. And that should give us a 0 here. But the rest of them we'll have to figure out. Minus 3y plus 3y, here is a 3y. Minus 6z minus 5z makes up minus 11z. And then finally, we have minus 27 plus 0, minus 27 right here. Okay, and you might do something to kind of indicate these are all one system. These go together, or you might not. It doesn't matter because we're not going to be using this method for long. Alternatively, kind of strike a line there, and I'm going to go after this again. All right, now remember what really made this pretty easy up here is I had a leading coefficient of 1. So I'm going to try to get a leading coefficient of 1 here, and then I'll be able to take multiples of this row and produce a 0 here and a 0 here. And the consequence will be this last equation will only have a z in it. The first equation will only have a x and a z, and then I'll be able to simplify further after that. So let's go after this one. What I'm going to do to get the 1. Now, if we were doing this numerically on a computer, we absolutely would not do it this way, but it's convenient for a hand calculation. I'm going to take minus 1 times this second row and add it to the third one. Now that won't give me the 0 I want, but it will give me a 1, and a 1 is easy to work with. So that's really the reason I'm doing this. So let's just copy this first one out. We're not making many changes here. That one stays the same. This second row is going to stay the same, but I'm actually going to write it in the third row place, and I'm going to take this this combination here is going to be in the place of the second row. So minus 2y plus 3y, of course we have zeros here, right? So minus 2y plus 3y gives plus 1y. And that gives that leading coefficient of 1 that's going to be real handy. Then 7z minus 11z is minus 4z. And let's see, plus 17 minus 27 will be minus 10. Goes here. And then this equation we're not really changing, but I am going to write it in the third row rather than in the second. Okay, and that's our second system. Now, what I'm going to do is use this leading coefficient of 1 to get a 0 here and a 0 here. That will get us a solution for z, actually, and we'll be darn close for the solution on y as well. But step at a time, let's go after it. So first of all, I'm going to take minus 1 times this row and add it to this row up here to get a 0 up there. So notice this leading 0 now, no matter what multiple I take of the second row and add it to the first or to the third, it's not going to change anything in the first and third columns because we're adding or subtracting multiples of 0. So this initial column here is actually predetermined. We know that it's going to look like that. But now I'm going to take minus 1 times this row, add it up here. So minus y plus y gives me 0y. And you could just call it 0, I guess. And minus times minus 4, we have 4 plus 2, 6z. And let's see here, we have 10 plus 9, 19, goes up here. This row, second row, is not being changed on this pass. So plus 1y minus 4z equals minus 17. And then we're going to take a minus 2 times this row, add it to this row, and that's going to go down to the bottom here. So I have minus 2y plus 2y, that produces a 0. Of course it does, that's why we're doing this. Then minus 2 times minus 4 is 8, minus 7, 1z. Or you could just say z, that'd be fine. And 20 minus 17, I get a 3 here. Now, this is actually some real progress. This tells me that I know the value of z in the solution. Z is 3, and I could take that 3 and plug it in here and actually get the solution of the other two. But for now, we're going to continue on in this style. So I'm going to take plus 4 times the bottom row added to the second row. It'll put a 0 there. So actually, why don't I do the top one first, and because that'll be easier to keep my row straight. So I've got minus 6. Well, these are not going to change, right? I'm going to take multiples of 0 and add to other things in this column. So these first two columns are already fixed. And it's really the last two columns that are going to change. So minus 6z plus 6z, that gives a 0 here. And again, of course, that's why we're doing this. We want a 0 up there. But this we have to compute. Minus 18 plus 19, that gives me a 1 up here. And let's see, we've got the next thing. We're going to multiply this row by plus 4. So I've got 4 times z plus a minus 4 times z. That's going to give a 0. And 4 times 3 is 12. 12 minus 17 is minus 5. And then finally, z is 3. Actually, I think there's an error here. I was expecting a 2. So let's see if we can find that. It's right here. That's supposed to be a 10. And it was just it's just a copying error. 0, 1y minus 4z minus 10. That row is not changed. And I got offline and grabbed the 17 instead of the 10. Okay, and now we should get the right value here. We have 3 times 4 is 12, minus 10 is 2, which is what I was expecting, and you can see why I could remember the solution. The solution is x is 1, y is 2. That almost looks like a negative 2. Let me make it clear that's a plus, and z is 3. Okay, now what I want to do is kind of strike a line here and show you a shorthand way of writing this solution. So I suppose write down the final conclusion. X is 1, y is 2, z is 3. Okay, now we can actually save ourselves a lot of trouble by not copying so many symbols. If you think about it, the way this is set up, the x variable is always in the first column, the y variable is always in the second, the z is in the third, and the constants are always on the right hand side. So really all I need are these numbers, which are the coefficients on the variables, and then the numbers on the right hand side. So this is another way of writing this system. I could just copy these coefficients, 1, 1, 2, 9, and these coefficients, 2, 4, minus 3, 1, and then finally 3, 6, minus 5, 0. And we should be able to see that same pattern right over here. 1, 1, 2, 9. Whoops, it's here. 2, 4, minus 3, 1. And then 3, 6, minus 5, and 0. Now, what I'm going to do is try to get these, this style of writing to match up with these things over here. So what I did on the first pass last time is I took multiples of this first row, added to the second and the third row to get a 0 here and here. So I'm going to do that again, and I'll write my multiplier over here for now. I want minus 2 times that first row, add to the second row. So the first row is not going to change. 1, 1, 2, 9. I'm going to take minus 2 times this row, add it to this row. Minus 2 plus 2, of course, is 0. That's the reason I'm doing this, is I want a 0 here. Then minus 2 plus 4 is 2. Minus 4 minus 3 is minus 7. And minus 18 plus 1 is minus 17. And we kind of expect some parallels here. 0, 2, minus 7, minus 17. This means this. Okay, and now I'm going to do the same deal, except I'm going to take a minus 3 times the first row, add it to the bottom row. So we get a 0 here, of course, and then minus 3 plus 6 is 3. Minus 6 minus 5 is minus 11. And minus 27 plus 0 is minus 27. And these should agree, 0, 3, minus 11, minus 27. Okay, now we have got what we wanted. We have a 1 here and zeros everywhere else in the column. I'd like to get a 1 here and then zeros everywhere else in the column. We'll take the same steps as last time though. I'm going to take minus 1 times the first row, add it to the third to get a 1 there. And then I'm going to switch the order of the rows. And I'll do that all in one step. So minus 2 plus 3, of course, let me write out what I can. Now I'm going to be over here, I'm going to be taking multiples of 0 and adding down here. So that's not going to change that at all. But everything else is going to change. So I've got minus 2 plus 3. That gives me the 1 that I'm after. 7 minus 11 minus 4. And let's see, 17 minus 27 minus 10 there. And then this second row is going to be written at the bottom. And we should see a pattern here. They should agree. Looks like they do. So this means this. Okay, now I'm ready to use this 1 to get a 0 here and here. So I'm going to start out with minus 1 times the second row, add to the first. And keep in mind, we're going to be taking multiples of 0, adding up here and down here. So that first column will not change. But the rest of it we need to pay attention. Minus 1 plus 1, of course, is 0. That's why we're doing that. And we're going to eventually, we're going to take minus 2 times this row added down here to get a 0 there. So we actually know what the first two columns are going to look like before we start. But here we got to work. 4 plus 2 is 6. And then 10 plus 9 is 19. And now I'm going to multiply by minus 2 and add down here. So I've got minus 2 plus 2 is 0. Then 8 minus 7 is 1. That's pretty handy. And we have 20 minus 17 is 3. And we were not changing the second row, so let me just copy that over. And that should agree with this. 0, 0, 1, 3, 1 minus 4 minus 10, 1, 0, 6, 19. So this means this. Okay, we are almost there. We want to get a 0 here and here, and we'll be able to read the solution. So I'm going to take 4 times this bottom row, add it to the row above. And actually, it's probably for a convenience of writing, I'm going to go after the first row first, just so that I get things lined up and don't have to erase when I get done. So I'm going to take out that 6 first. So multiply by minus 6 and then add. So first two columns don't change because I'm going to be taking multiples of these zeros and adding to these columns here. And adding multiples of 0 doesn't make any changes. And of course, that bottom row is already in its final form. Okay, so here we go. Minus 6 plus 6, I got a 0 up there. And then minus 18 plus 19, I got a 1 here. And then let's see, I want to take out that 4. So I'm going to multiply by plus 4 and add. So 4 minus 4, a 0 goes here. 3 times 4 is 12, minus 10, a 2 goes there. And this is our final form of our matrix. And notice it says just what that does over on the left. X plus 0 equals 1. 0 plus y plus 0 equals 2. And 0 plus 0 plus z equals 3. So our solution is, this is the x column, the y column, the z column. So 1 times x equals 1. X is 1. 1 times y plus zeros is equal to 2. So y equals 2 and z equals 3. And that's the solution. Okay, this method that we're using over here, where we put things in a rectangular array, first of all, this kind of an array is called a matrix. And this process of trying to get ones and zeros in propitious places, that is referred to as row reduction. And the whole process here of representing this in a matrix, row reducing it until you get down to this form, this system is known as Gaussian elimination. I've also seen resources that refer to it as Gauss elimination. And that's an N, not an M. It's Gauss is the name, of course, of a famous mathematician. Okay, so this is the style that we want to use. This is cumbersome. It involves writing a whole bunch of things that we don't need, and this is just more practical. Furthermore, it's possible to clean some things up on this and make it actually work well on a computer. Now, it's not exactly like this, but this is the idea behind what goes on in the computational work. Okay, second page, we have two more systems, and we're going to try to speed up a little bit here. So I am going to write this as 1, 1, 2, 9, 2, 4, minus 3, 1, 3, 5, minus 1, 10. That's our matrix. And what we're trying to get is ones down this diagonal here, zeros below and above, and then whatever pops out over here will be the solution. X equals the first one, y equals the second, and z equals the third. Now, keep in mind there is a possibility that this could fail. Namely, you could get, say, a string of all zeros down here in the bottom, which means that we wouldn't be able to determine a single value for z. Or you could get something like this, 0, 0, 0, 10. If you got that, that would say 0 times x plus 0 times y plus 0 times z equals 10. Well, clearly it does not. That would indicate that there is no solution to this system. So we'll work through these two, and then I'll show you how to interpret the solution at the end. Okay, so I've got my leading one right here. That's what I want for this row. So I want a zeros here and here. I'm going to start in with the multipliers and the adding. I usually use like a tilde to indicate that this is row equivalent to that. In other words, I'm using legal row operations to get from here to here. And furthermore, more really important is to say that they're row equivalent means that if these are representing systems of equations, those two systems have exactly the same set of solutions. And so we just keep transforming until it's easy to read the solutions, and that gives us the solution of the original one. Okay, we are not changing the first row, 1, 1, 2, 9. And then I'm going to take minus 2 times the 2 here. I'm going to get a 0. And thinking ahead, I'm going to take a minus 3 times this row and add it here to get a 0 there, right? That's the reason I'm doing this, is I want that pattern. So I actually can predict what's going to happen. And if I don't get that, it's because I made a mistake. Okay, minus 2 plus 4 is a 2 here. Minus 4, minus 3 is a minus 7 here. And minus 18 plus 1 is minus 17 here. Looking familiar so far, but this bottom equation is different from the one that we had before, so it won't be just a repeat all the way through. Okay, I'm going to take minus 3 times the first row, add it to the third to get that 0, and then I'm going to take minus 3 plus 5 is a 2 here. Minus 6, minus 1 is minus 7, and then let's see, minus 18, whoops, minus 27, plus 10 is minus 17. Aha! If you're clever and looking ahead, you can see what's going to happen to me here. When I try to get a 0 here, I'm going to take, in this case, you could use a minus 1 times this row, add it to this, but all those entries match exactly, so I'm going to get a row of zeros at the bottom. So we might as well go ahead and take that step now, because it simplifies the matrix, and we know sooner or later that's going to happen. So, whoops, not minus 2, minus 1 times the second row, add it to the third row, and we're not making any changes to the first one right now. I'm just anticipating what's going to happen here. This one will not change, but this one is going to be completely wiped out. Another way of looking at that is there's no information in this third row that isn't already in the second. So you can just throw away the third row. It doesn't tell us anything new. Everything we know about this system comes from the first two equations. Now, at this point, we're probably kind of stuck working with fractions, or we have to just start doing some manipulations that are really kind of strange. So I am going to go ahead and do fractions here. I'm going to take this row and multiply it through by 1/2. And of course, the bottom row is just a string of zeros. And I'm just copying the first row. Of course, you could combine some steps here if you wanted to, but I'm trying to make this followable. And then I'll take -1 times this first row, add it, rather to the second row, add it to the first row, and that is going to get our system as good as we can get it. So essentially, it's this row minus this row. So I've got 1, 0, that minus that, that minus that. Let's see, 4 halves plus 7 halves, 11 halves. And then 18 halves plus 17 halves, 35 halves. This row is just what it is. And that's as close as we can get to that preferred standard. What we'd really like, of course, is to get ones down here, zeros below, zeros above, and then just whatever we get in the right-hand column. We can't get there this time because there's no way to get a 1 here in order to clear out this entry and this entry. Now, when this happens, it is not disaster. We are still going to be able to solve this system, but it's going to be easier to see why I do what I do if I take a couple extra steps. So I'm just going to take a couple of steps here that eventually you'll be able to skip, but it makes the explanation a lot simpler. So remember, this is x's here, y's here, z's here, and then we have equal signs, and that's the right-hand side of the equation. So this says x plus 0, or you could say 0y, wouldn't matter, plus 11 halves z is equal to 35 halves. This one says 0 plus y minus, well, so much for that mechanical pencil. This is the night for technology, I'll tell you. That is actually the second blowout on a pencil I've had too. Okay, so minus 7 halves, third, I'm running short, minus 7 halves z equals minus 17 halves, and I've got a row of zeros, which you may as well just ignore. It doesn't have any information in it. Okay, now, boy, that's hard to read. That says 11 halves right there. It looks almost like 4 halves. And now it looks smeared, so that's probably not better. Anyway, we'll get it on the next line. Now, I can solve this for x. It says x is equal to, let's take this one first, 35 halves, that's the right-hand side, minus 11 halves times z. And this says that y is equal to minus 17 halves plus 7 halves z. And Z, well, we don't have any information about that at all. So the tradition is to change letters here. I don't know why, but we do. So now notice this has the pattern a constant and then a multiple of something else. So I'm going to follow that pattern here, and you'll see why in a minute. I'm going to say, well, I don't have any constant over there except for the 0. So I'm going to write the 0. And then I am going to say, rather than calling that Z, I'm going to take a new letter, and it's just tradition. These are usually done with like T, R, S, and letters nearby in the alphabet. Now, if I just do a replacement, this is what I have. 35 halves minus 11 halves. That Z, we're making that T, right? Minus 17 halves plus 7 halves Z, but Z is the same as T. And this one, and you'll see in a moment why I want the 0 there. 0 plus 1T. This version is known as the parameterized form of the solution of this system. And what you can see here is that there's actually infinitely many solutions. I can pick any number I want t to be. So for instance, if I set t to 0, all this drops out, right? And then x equals 35 halves, y equals minus 17 halves, and z equals 0. But I could also just as well set z, say, equal to 1. In that case, x would be 35 halves minus 11 halves, or 24 halves, 12. Y, if I set t to be 1, would be minus 7 halves, minus 17 halves, minus 7 halves, minus 10 halves, 5. And then z would be equal to 1. So there's another solution. The point is this. T is a free choice. And for every one of the choices we make for t, we get another solution. It sets values x, y, and z. And if you took those values x, y, and z and plug them back into the original equation, you would find that it would solve it. So t is a free choice, and we have infinitely many solutions. Okay, now remember the first one we did, we had a single solution. There's one and only one solution here, so we usually say that this is a unique solution. Here we solved our system, and it turned out that we had infinitely many solutions. And when we solve this one, we're going to find out the only other remaining case, which turns out to be a case where you have no solutions at all. So let's go after that one, and we'll see how to row reduce, and then how to interpret the results. So I'm going to start out by converting this to a matrix form. So I'm looking way up here, 1, 1, 2, 9 for my first row. Second row, 2, 4, minus 3, 1. 2, 4, minus 3, 1. And the third row, 4, 6, 1, 1. 4, 6, 1, 1. Okay, and now we are going to row reduce, or you could say we're going to perform Gaussian elimination on this matrix. So I'm going to take minus 2 times the first row, add it to the second. Now, if you just think about it for a moment, I believe these are exactly the same rows that we had last time in the first two locations. So we already know what's going to happen. The first row is not going to change on the first step. 1, 1, 2, 9. The second row is going to become 0, 2, minus 7, minus 17. And it would be good practice to check that out, make sure that that's right. And then the third row is different because this bottom equation here, let's bring that down a bit, this bottom equation here is different from this equation. So we have different numbers in the matrix. So looking at my matrix, I'm going to take minus 4 times that first row, add it to the third row, and let's see what we get. Get a 0 here, of course, that's why we're doing it. Minus 4 plus 6 is 2. Then minus 8 plus 1 is minus 7. Starting to look suspiciously like what we saw before, right? We're duplicating that bottom row. Well, something different happens on this step, though. 9 times 4, 1836 minus 36 plus 1, 35. And I'm kind of running into my stuff there, so I'll just come down because we just have one more step before we get to the critical observation. I'm going to take minus 1 times the second row and add it to the third because I know what's going to happen. And that's it's going to tell us what's going on with this system. So we could, of course, get a leading 1 by dividing this through by 2, but it turns out it won't be. It would be wasted effort in this case, and you'll see why in a moment. Okay, so minus 2 plus 2, I'm going to get a 0 here. Then 7 minus 7, I'm going to get a 0 there. But here I get 17 plus 35. And anyway, this is not 0, right? 53 is what I'm getting here. I wonder if there's a mistake. I don't remember that number from before. Anyway, this is the pattern that we need. We're getting 0, 0, 0, and a non-zero number over here. So if you were to interpret this, this is what it says. 0 times the x variable plus 0 times the y variable plus 0 times the z variable is equal to some number that is not 0. That's really all that matters here. And that is a contradiction. Of course, this is not true. You can't take any three numbers, multiply each one of them by 0, and add up and get something that's not 0, right? So that's an impossibility. We've got a contradiction here, which means that there is no solution. And it turns out that that is exactly the three possible cases when you solve a system of linear equations. This one had 3 equations and 3 unknowns, but it turns out it doesn't matter how many unknowns and it doesn't matter how many equations you have. You will always land into one of these 3 cases. You could have infinitely many solutions, you could have no solution at all, or you could have a unique solution, and that is all that is possible. So we're going to let that go at that, and I will make a separate recording for the next page that starts talking about elementary row operations. Before I go, though, there's something I almost forgot, and that is that when we have our solutions in this form, we can also represent that with vectors. So let me show you how to do that. This one, of course, is pretty easy. The vector xyz is equal to 1, 2, 3. So there's one and only one vector solution for this first system of equations on the first page. We had a unique solution. That's what you'd expect. On the second page, however, we have this form, and I never really got to the punchline there. So let me write the vector solution of this. We have xyz again, of course. So I'm just going to flip over. xyz is equal to, and the reason that I was so careful to keep the constants here and then the multiples of t here, is that allows us to translate this directly to a vector format. So I have 35 halves minus 17 halves, 0. 35 halves minus 17 halves, 0. And then t times another vector, and that vector is minus 11 halves, 7 halves, and 1. And this is the vector form of the solution of the system of equations, the second one that we did. The third one, there really isn't a way to write that with a vector because remember, there's no solution. In other words, if you were going to write down the set of all vectors that solve this system, it's the empty set. So I suppose if you need to write something, you could write that. It's the empty set of vectors that solves this system. But in this, being able to translate this parameterized form to the vector form really is important. And if you look, it's all I'm doing is if I get things lined up properly in here, then it's really quite easy to do. This is the constant vector, which occurs here. And this is the vector of coefficients. This is the vector of coefficients on t, which occurs here. So this is not unlike the form y equals mx plus b, right? You've got a variable here, a variable vector, a coefficient of sorts times a variable, and then a constant being added. So this is the vector form, and you will want to know how to do those as well.